everybody. Thank you very much for joining us here today. Paul Taubman with 9.Connects. You are in the right place if you are here for our webinar on xSignals and match length tuning. So we have two presenters today. I myself, Paul Taubman, will be doing the tool handling aspect of both the xSignals and the match length tuning. Joining us today also is Tom Cassidy. Tom is on our services side here at 9.Connects. He's had a lot of experience, especially during the past year, with DDR3 and DDR4. And he's agreed to come on today to show a couple of real-world applications. So what we're going to do here for our objectives, first and foremost, we'll talk about xSignals. Then I'm going to give a quick primer on differential pairs, because if you're going to do match length tuning, a good portion of that may actually be done on differential pairs. So we should just take a look and to better understand how we can set up our differential pairs. Then we'll go into the match length tuning aspect of that. One housekeeping note, we've gone through this webinar presentation, our preparation for it, several times, and we may actually go to the hour. So we may not have time for questions. However, if you do have a question, please do put it into the questions box of the GoToWebinar panel. We'll be more than happy to take a look at that afterwards. And if we have enough questions, we'll certainly put together a global Q&A. Other than that, we may just get back to you on a one-on-one basis at that point. So please do ask those questions. We certainly are curious to know what you're interested in. So we're going to jump into our first polling question over here. So let's get that up here onto the screen. All right. So take a look at that here. We're just kind of interested in knowing what your primary role is. All right. So we're going to close the poll over here. And this is actually a really interesting thing that we have seen over the past decade or so. If we had probably given this about 10 years ago, I think those numbers would have been switched. Right now, it's showing about 36% of you are actually PCB specialists. These are the things that you do day in, day out. We have a number of electrical engineers who are becoming also they're becoming more and more PCB layout artists, in addition to the circuit design type of things they're doing as well. And then we notice that there are those who are probably call themselves systems engineers, where either you are actually a true systems engineer, or if you were like me when I worked in the defense industry, you were the go-to guy to do a little bit of everything, right? You're the knowledge person just to kind of keep things moving along there. So that's great. We really appreciate that. We do have one more poll that we're going to do here before we get into things. So let's get that poll up here. And we're just kind of curious to know if you've actually tried your hand at high-speed design. All right, so we're going to close the poll over here, and we can see that there's almost an equal amount of those who are doing it all the time or just starting to dabble into it. So that's definitely good. And then, of course, there are others who are just starting to look into it. I hope that for those who are just looking into it or just looking into the tool, that you find this webinar very useful. So with that, I'm going to start off here. So I want to talk about some terminology here for a moment. There's a lot of discussion about length tuning and length matching. And I want to talk about length tuning here for just a moment. So I'm going to roll this back over here. Length tuning is, from our definition, is the purpose of length is really taking a length of a single signal and adjusting it accordingly so that it is going to be within the design parameters. And what do you mean by design parameters? It may be a length necessary for a bus protocol, or it's a length necessary in order to get something to the receiver in a period of time that is required. And we're giving a very, very general definition over here, but the time is the length times the propagation delay. And we've done plenty of webinars in the past to talk about propagation delay. That all happens to do with impedances and the way you set up your boards. But the other element of it, and which is what we're going to spend some time on today, is the actual length of it itself. So when we're talking about length tuning, we're usually talking about an individual signal, as opposed to length matching, where you're taking a group of signals and you're trying to get them all together so that they are within a certain tolerance. So, for example, two signals within a differential pair, or something like the bits within a data byte. So what could happen there is that if one of them has to be longer than the others, just because of the topology of your routing, the other ones have to be matched up to that so that they all arrive at the same time. Here's the point. We may use these interchangeably throughout this particular webinar. So if we do kind of use the terminology incorrectly, we do apologize. It's something that kind of dawned on us as we were getting ready for this webinar here in the last 24 hours. Now, what I'd like to do here is we're going to start off into xSignals. And really, for us to do match length tuning, we've got to understand the xSignal aspect of this. And before we go on, I'm just kind of curious to know if you have done some xSignals in the past. So we're going to get that polling question up over here. Okay, so Looks like some of you have been using it all the time. Hopefully I'll show you a trick or two that you haven't seen before. A lot of you are starting to dabble in it, and I hope that when we are going through this over here, you'll get a few ideas as to how to make it work for you. And I do see a good portion, almost half of you are just either starting to look into or just interested in the capability of the tool. So let's take a look at this. First and foremost, the whole idea of calling an xSignal means to cross the signal. If you're familiar with Altium Designer, in the past, if you wanted to do something from point A all the way over to point B, you would have had to keep a spreadsheet, because if there was something in the middle over here, Altium was not able to compensate for that in terms of its path. So you would have to have kept a spreadsheet for bus 1, you would have had to keep a spreadsheet for O bus 1, and of course for the other signals here as well if you're trying to do match length tuning. xSignals allows me to create a, let's call it a signal. It's kind of almost like an imaginary signal that goes from 1 all the way through 4, so that Altium recognizes the fact that even if there are components in between over here, it will still consider it as to being a complete net. And that is the whole idea of the xSignals. So with that, I'm going to get out of my PowerPoint presentation and show you some stuff here in Altium Designer. So when it comes to xSignals, you can do it one of two different ways. You can do it in what I call a linear fashion, and this is what you see here where you've got series termination, or you may also have T-junctions as well. Now, in the past, what a lot of people used to do prior to xSignals is that if they were going to do some type of accountability in some type of spreadsheet, they wanted to have individual signal names. And the only way you could do that in Altium is you actually had to put in a junction, one that you created on your own over here, in order to maintain those names. xSignals does not require this. So if you still want to keep your names, you can still put these in here, but for the purposes of xSignals, you don't have to have it. And as a matter of fact, I'll demonstrate that a little bit later on, where I've removed all of those junctions here and just let Altium do the wire ORing here just by the, auto junction here by just connecting the wires together. Of course, at this point, all of these are going to be called node_JT_A, but again, if I don't care about that and I can remedy this through the xSignals, all the better. So that's what we're going to take a look at here. In terms of setting up xSignals on the schematic side, there's really not a whole lot you can do here. This is really handled on the PCB dock side. So let's jump over there right now. So in the PCB dock here, I've set up a couple of examples. Let's take a look at our linear example here, where we go from P1 into a series resistance, then into P2 over here. If I just want to create an xSignal, it's pretty straightforward and simple. I can click on 1 here. So let's zoom on in here so you can see this. So I'm clicking on P1 pin 1. So I've got this highlighted if you can't see it. And then I'm going to pan over. I'm using my right mouse to pan over here. I'm going to hold down my shift key and I'm going to select P2. If I right click on P2 over here and I go down to xSignal, so it's a right click xSignals, I have two options. I can run the xSignal wizard, or I can do create signals from selected pins. And I will show the xSignal wizard here in a moment, but just for our purposes, if I want to create one that's quick and dirty, I can just do create signals from selected pins, and boom, it is now done. I don't know how well you can see this on your screen over here, but what's happened here is the rest of the screen has gone into a dim mode, and it now is specifically showing me the line from P1 all the way through R1 and into P2. If I want to monitor these things, I need to have my PCB panel up. So here's my PCB panel, and make sure it is on the drop down for xSignals. In the categories here, it's kind of the same breakdown you see for all of these type of things for components and nets and so on and so forth. You start with your classes here first, then you talk about the actual, in this case, the actual xSignal, and then you show its individual components that make up the xSignal. One side note over here, that even though you can see these and you can click on them to see where those nodes are, you cannot delete these here. So if for some reason you don't like the path you take, you will have to delete it. That may happen here a little bit later on the junction as I demonstrate that part of it. But now I've got it, all right? So as long as I've got this here, let's take a look at the name. You can see it says bus 1 to O bus 1 underscore PP1. So it's taking the net name from the first side, taking the net name from the other side over here, and then just basically combine them together to call this the xSignal, and then PP1 means point to point 1. All right, now what if I want to do a lot more of these than, so let's say I've got, several dozen of these. I don't want to have to go on here and click on these things back and forth all day long. So another way we can do this is through the wizard, and I'm going to do a Shift-C here to clear out. So, and I'm just going to click another pin here. As a matter of fact, I can even just click the part itself. So whether I click on a pin or a part itself, if I right click and I go to xSignals here, I have a few more options. But the one I want to run over here is the run xSignals. Just as a side note, so the one we ran before was from between components, and then this create xSignals from connected nets is really an older version of the xSignal wizard. So we're not going to spend any time with this because the newer xSignal wizard does a really great job, and I'm going to walk you through it. And also Tom is going to show you an element of it as well. So I'm going to click on that here. Here we are in the wizard, and I'm going to press next. So there are three different wizards. Remember, the whole idea of a wizard is to walk you through a certain type of capability of the tool here. Tom's going to walk you through the DDR3 and the DDR4. We simply won't have time to look at the USB 3.0, but if you're doing 3.0, take a look at it. It will walk you through it. The one I'm going to do is the more generic custom multi-component interconnect, where we have a destination, we have some chips in the middle, and we have our source, some chips in the middle, and then our destination over here. So let's click on next here. It's going to ask us, well, where do you want to get started? So I don't have to necessarily start over here on P1, all right? And what I'm going to do here, this is basically nothing more than a filter. If I click this, I can see every single header that I've got in this example here. But if I type in P1, it's going to basically shorten up the list. It'll show you its pin count. So if you want to filter on the number of pins, and of course this layer as well. For this purpose, this is a through hole, so it's not a really big issue here. But we're going to press next here. Now it's going to say, okay, I've looked at your part here, and according to this part, you've got 4 net labels. So we need to select those. So I'm going to select the first one, hold down my shift key, and grab those over here and press next. Now it's going to ask me, okay, let's delete this over here so you can take a look at this. It's going to ask me where my destination is. And you can see it already kind of mentioned P2 over here, but in theory, I could actually create an xSignal for everything, even if they are not connected through the schematic or the net list itself. I would very much caution you on that. If you are trying to create new net basically new net paths that didn't exist in your schematic, I would go back to the schematic and correct that before you go on. The xSignals will let you do it, but it gets kind of messy, and I wouldn't recommend it. For this purposes over here, though I zoomed it in, P2 is on the other side. I'm going to select that. So now I have my destination here, and I'm going to press next. Now it comes back and says, okay, from there I can create these 4 xSignals. So the names should look remarkably similar to what we have over here in the PCB panel. Notice that this one is called PP2 as opposed to PP1 because PP1 exists. So when you use the xSignal wizard, if you have these things already in existence, so some type of xSignal in existence, you can create duplications. I would advise against that, because if you've ever dealt with rules and you've ever dealt with classes and you've ever dealt with situations where you can put multiple things, the same thing, into different classes because classes are not mutually exclusive, and you start using those different classes with those same elements in it in your rules, it turns into a very tangled web. And this can certainly happen with xSignals as well. So I would caution you on just randomly making xSignals. You may want to use the wizard first to organize those and then create the ones that you need to do afterwards, knowing that they do not exist. Because as I said, Altium's not going to delete this one here by default. So one of the things we can do here too is we can create a class. And if I don't want to use this class, I can say, well, no, I don't need the class. I'm just going to dump it into the all xSignals. And of course, if you're familiar with classes in Altium Designer, there's always an all for each one of those type of classes. So for component class, there's an all. For the net classes, there's an all. And there's the same thing for here for xSignals as well. So if I don't want to have a separate class, that's fine. I don't have to. I can just put it under all xSignals. So I'll create it just so that we can see it here afterwards. I'm going to press next. So one of the things that the wizard's now going to ask me is saying, well, do you want a rule for this? And of course, generally speaking, I do want to have a rule because that's really one of the reasons I'm setting up the xSignals is to match length tune. And the match length tuning, I have the option of doing it based on a rule. So it's going to show me, it's like, look, here are the signals that you've got. Here is the class that I'll create. So I'll actually create a separate class for these 4 xSignals. And this will be the name that it will give me under what is called the match length rule under the high speed category in the rules. So they don't really give you a button to look at that particular rule. They basically say, hey, this is the name we're going to give it. And if you ever look at that rule, and we'll do that here in a couple of minutes, it's going to ask for nothing more than a length tolerance anyways. So for all of these here, we're going to say that they are going to be under this name using this class. We don't have to list each one of these separately, or Altium doesn't have to list it because it's going to create it for us. And then we're going to have a length tolerance of 100 mils. I'm just going to change this because in a moment here, you'll see why. but I'm going to say it's 75, and then I'm going to press next. So now what Altium offers me the opportunity to do is to do match length tuning based on the source up to the first resistance, or pardon me, series of resistors. And as you can figure out in a moment, it's going to also ask me from the resistors all the way to the destination. So why is that? Because in match length tuning, I may actually have to match length tune for three aspects: the overall, the approach up to each one of these resistors, and then from the resistors, the approach all the way to the destination there. So if I click on yes here, you can see that now it's going to say, do you want another rule for this? And I'll say yes. So it creates actually another class here. It's going to create another rule name here, and it's going to create another tolerance. This one I'm just going to call 50, just so we can see the difference between these afterwards. I'm going to press next. And of course, as I mentioned, there's also between the individual resistors and the destination, it gets yet again given us another X class name. By the way, we can change these if these are too long or you find them kind of difficult to read. The same thing with the rule name itself. This one here for grins, we'll just call it 25 mils. All right, and I'll press next. So by the time we are done with this, when we look at this, we'll actually see 4 classes, because we created 3 of them for the rules and 1 generic class as well for the ones that we selected in the wizard. And if I want to, I can continue creating more classes here, so I can continue doing this, because again, even though I started on P1, I don't have to do everything on P1. I can do it on any of the other headers or any of the other components that happen to be there in my design. But for now, I'm going to click on a finished wizard, or we're going to have the finished wizard radial selected, and I'll click finish. Let's take a look at what we got here. So you can now see, and let's zoom this out so you can see these highlighted. All 4 of these are now highlighted. Okay, so I now have all 4 of these xSignals, and I am looking at the generic xSignal class that I created. If we click on all signals, we're going to see a whole bunch of them. So why is that? Because when we created each one of these rules, or pardon me, classes here for those rules, they also created a couple of other buses here. So these obviously match up with existing ones. But when you look over here, this was the new rule that was created from the source all the way over to the resistors. And then, of course, if I click on this one here, you can see the names change because it goes from the resistors all the way to the destination. Now, if you do not like what you saw in these rules over here, you will need to close out Altium's PCB doc and don't save it. Because if you later on want to delete these things, there's going to be a little bit of a procedure for that, and I'll show you that here in a moment. Let me also show you the rule, since we're here. Let's go to Design Rules. And under the match length, you can see that these 3 rules got created here. Let me bring it up so you can see the category in general. I also did this here so you could see that, yes, when I put in the 75, that was matched with this one, the 50 matched with this one, and the 25 matched with this one here. Let me see if I can pull these out so you can see them a little bit better. Unfortunately, I don't have a whole lot of stretch there, but there you can go, and you can see each one of these classes was created over here, and now they're represented as part of the rules. So they are instantly put into the rule set. What if I want to get rid of these? If, let's say later on I've turned this into total hash, I want to start again. If I do that, then what I have to do, and let's say this is much after you've done the xSignal wizard, you can click on all signals, and then you can delete them all. So if we select the first one in the list, and we hold down our Shift key, and we click, we can delete all of these over here. We'll say yes, and so these should all go away. Now, unfortunately, the classes and the rules still exist. The easiest way to get rid of these classes here is actually in the PCB panel, not in design classes. In design classes, you'll have to delete these individually. But from here, I can select the first one. I'll select the second to last one. Remember, the all signals is default. Altium's not going to delete that. I'm going to right-click this, and I'll say delete selected classes. Those are now gone. And the last thing I'm going to have to do is go back into my rules here. And unfortunately, when it comes to rules, I have to do each one individually. So when I select these, I have to right-click and say delete the rule. So just be aware of that. I'll press these rules and say yes. That's pretty much the way you would have to clear out the xSignals if you want to start again. So be aware of that. Let's talk a moment about the junctions. As I mentioned earlier on, you do not have to have a component junction anymore unless you're trying to maintain the net lane. Here I'm going to zoom in a little bit, and you can see that in this first example, there are no junctions in here. So they are all called node TJ_A. So whether I do it over here or I jump down here and zoom in enough, we can see that they're all the same, and that's perfectly fine. For Altium's purposes, the same way we did it initially is the same way you can create these branches here. So you can click on P13, this pin here. I'm going to hold down my Shift key and click on P14 right-click xSignals and create signals from the selected pin, and voila, there it is. The exact same thing will work over here in the, let's do a Shift-C here so we can clear this. Here's an example. It's very similar to what you saw on the top, but in this particular instance, I actually do have a junction. So there's a symbol and the corresponding footprint for this junction over here, and this allows me to maintain the net name if I want to do that. But again, as I mentioned earlier on, you do not have to do this for xSignals. It's really more for your own readability purposes. So if I pick one here like P11, and I go over here to P9, I'm going to click, pardon me, shift click. Let me do that again because I pressed the wrong button. Here's a Control-C to clear it. Let's click that one. Let's pan over with my right mouse button. Let's hold the Shift key, right mouse click, xSignals, and create xSignals from the pin. Now, the reason I bring this up is I've seen a few little issues here with the current version of Altium. If this is broken over here, this usually means that either you were trying to, either just didn't read the net list properly, for some reason it's been happening a little bit here with this particular version, or you were trying to get two things together that were never part of the net list to begin with. This is a part of the net list. What I have found is that in this situation here, you do have to delete it. And the simplest thing to do is simply close this. So let's close this document. I will save what I've been doing so far. I'll press yes, and I'll go back to my project over here and double click and open it again, and it should work this next time. So let's bring that back up here again. And you know, that's a little bit frustrating. I know you're saying, crazy Altium. But the fact of the matter is that if you had to keep a spreadsheet with this moment of inconvenience is really minor compared to the amount of hassle and effort you would have had to do to, you know, basically maintain a spreadsheet for all of these signals. So, you know, it's going to improve over time, and there it is. So let's do this. Right-click, xSignals, create the xSignals from the selected pins, and boom, now it works. So just want to let you know it certainly does work, even if you have the individual wires and you have these little connectors in between at this point. So there it is. One last note before I turn this over to Tom. If for some reason it grabs something weird, or you want to somehow modify this, you cannot do that. And let me just bring this back here. So here you can see these are all the individual primitives that make up that xSignal that you can see over here. Unfortunately, there is no way to delete any of them. So sometimes what may happen is that it may actually grab an additional branch. If that is the case, you will have to delete it and give it a go. A lot of times what will fix that is if you went from, let's say, pin 8, pin 1 to pin 9, pin 1, and you get some weird effect, sometimes the best thing to do is delete this and then try to go from P9 over to P8, and that might correct it at that point in time. So just be aware of it. What we have found is that generally speaking, when it comes to things that are linear in nature, where you're going from point A to point B to point C to point E, it works just fine. When you start getting into junctions, there are a little bit of issues that we have seen with those in the past. So just be aware of that. Again, over time, Altium will probably fix and remedy those things here rather nicely. With that, I am going to turn it over to Tom, who's going to show you a few more things with the xSignals here. So Tom, I'm going to give you the, I'll make you the presenter.
Okay, thank you, Paul. Hopefully you can see my screen.
And I can hear you just fine, thank you.
You hear me fine, great. So I'd like to show some real world examples, mostly focusing on the world of DDR3 memory, since that seems to be a common thing nowadays. Back in the old days, before we had xSignals, there was a common use of net ties and requirements to have different net names in order to deal with the termination requirements of DDR3, specifically the addresses. You basically, when you're doing DDR3 and you want to length tune, you want to be able to tune between your source and the two chips, but you don't want to have to include the termination, trace, and resistor in your length calculations. And like I said, before xSignals came along, in order to do this, you had to maintain two separate net names, which would require the use of a net tie. So here's a very old design I had lying around where you can see I actually have some net ties in here. I have my address 14, goes through a net tie, and then I go to the terminated version of the address 14. What this will let you do is calculate from your source up to the net tie or up to the chip. Still a little bit awkward, but it was better than having to subtract out those traces. So if I go over to the circuit board, you can see here's my source chip, and then I've got my two DDR3 chips, and the addresses basically come off the left to come over here. So, and then up here in the upper right-hand side, you can see I have my termination. So what I like to do is length tune between this chip, coming over here, going across these two, but I like to stop and not go on there. So I've created a net, just a plain old net class that includes all those signals I was showing. Here you can see they come off of the FPGA, they come over, they go to the first chip, they go over to the second chip, but then they stop. And in this situation, the net tie shape that what made most sense to me was basically creating a version of a through-hole via, which would minimize my stubbing. But you can kind of see that on this one here, the signal comes in, goes through the via up to the pin, but then it would also have gone over on this pin to go over to the, or this trace to go over to the net tie, to the termination resistor. So nowadays it's a little bit easier. We basically do no longer need that. So here's the same design, but as you can see, I've taken out the net ties, and now the address net goes straight from the FPGA through the two chips and right to my termination resistor. So here's this updated version of the design. You can see it's basically the same thing. So what I'm going to show you now is how to use the xSignal wizard and one of the more optimized versions of it, specifically designed for DDR3. As you saw Paul presented earlier, you can do this manually where you can select the first source chip, select your destination chip, and then basically create all of the signal groups you need. Altium gives you a little bit better. So I'm going to hit some shortcut keys, DXW. Let me hit it, DXW. So here is the same wizard you saw Paul used earlier, but now instead of using the custom multi-component, I'm going to go up here to the onboard DDR3, DDR4. And this, like I say, is customized to help you lay out your DDR3. There's a little extra information you're going to need in this. I'm just going to kind of rush through it, but basically you have to tell it some information like the size of your byte lanes, and then you can give it some initial tolerances. There was a question I noticed earlier, someone was asking about this. These tolerances can always be changed. So even though you're entering them here in the wizard, it's very easy to go back into the design rules and make these changes as needed. So don't worry about blocking that in. So here in the wizard, once again, I'm going to choose my source chip, which is U1. And then down here, I actually get to pick my two memory chips. So I'm going to select both of these. So it's going from U1 to memory devices U2 and U3. Select that one. And now what it's going to say is it's going to ask me which topology I want to use. And there's basically two kinds of topologies with DDR3. There's the T branch, mostly used for when you're using DIMMs. And then there's the flyby. And this is what I want to use. Flyby basically means that your addresses are going to go from your source, cross one chip to the next chip to the next chip and so on. They're not going to be branched, just going to be one long line. So you can see here I'm picking U1 as the source. And Altium gives you the chance to order these. I'm going to put them in order 2 and 3, but for some reason you need to swap those, you can. And then it shows you these are the names it's going to give. You go ahead and analyze, and you'll see over here it created two columns. One for the address 1, which goes from U1 to U2. And then one for address 2, which goes from U1 to U3, basically flying by U2. In a design where I happen to have had maybe 4 memory chips, and I'd done this, you would have seen 4 columns, and each one would have gone from the source to the destination chip. So right away you can see this is doing a lot of work for you instead of having to go in and do that manually. So I'm going to accept that. The next page has to do with the memory, the data buses. You can see there's 4 data buses, since I told it was 8 bits. Also gives you the chance to name. I'm going to skip over this since I'm really just focusing on the addresses. So once that's done, you'll see over here in my xSignals that it's going to go through, it's going to analyze, and I will come up with 2 more xSignals groups over here. So group signal address 1, as you can see, goes from the FPGA, comes up and goes to the first chip and stops there. So this will let me length tune and do whatever kind of rule sets I need for that specific leg of the journey. Then I can come over to address 2, and you can see how it basically added on to the end of that. The first one stayed the same, of course, but now I've got another well set up class that I can now length tune the second length of addresses. Of course, as you can see, when you're doing your length tuning, you'll do the first one here, get that the way you want it, and then do the second one. Any changes you need to make, you of course want to use the signals between the chips. You don't want to modify the original signals, or you'll mess up your first one. And like I said earlier, if I had more than 2 chips, if I had another chip over here, I would have had address 3, and it would have added that little segment on, and so on and so on. And once again, as you see here, I'm terminating at the last chip. The termination resistors are not included in these calculations. So a very nice tool if you're doing some DDR3, and they also have a version for USB to help you some of the more specifics with dealing with the USB when you're going through their termination and protective chips. So this is an example of why you would not want to use net ties anymore. Let me show you an example of why you would. Suppose you have a circuit where you've got some high-speed signals and you want to basically measure that signal somewhere along the line. So here's a kind of a quick example. So I have a source A and a destination B. I've got some high-speed signals going across some differential pairs, although I didn't mark them as such. But and these signals in this design happen to be, you needed to maintain the phase relationship between the signals. So length tuning was not just for timing, but it was also for phase. You wanted them to both arrive at the same time or you'd get some phase shift. But the same thing happens if you wanted to tap into that, just another piece of copper coming off and going to, say, a high-speed analog digital converter or a buffer or something. You're not going to want to introduce any phase delay either. So you basically want the tap to be the same distance from A to the tap, and then from the tap on to B to maintain it. And you're also going to want to maintain the same length between these two so you don't introduce any phase offset in your tap circuit. So in this case, you do need to have a tap, a net tie, and a special footprint because it's basically all just copper. There's no actual component to go through. You need to actually put in an artificial component in order to maintain the different net names. So with this in mind, I'll go over here and I'll show you the very quick graphic example. Here's my source A. You can see the red lines in the top layer are my differential pairs going over to B. And these are offset, so it's not necessarily true that the distance from here to here is the same. There might be some, pin delays within the chip or some routing you needed to deal with. But you can see the net ties, and my taps are the signals in blue, and I'm tapping into the 4 signals here. So what I did was I created a special net tie that looked kind of like this. My plan was to have a via drop down from layer 1 to the bottom. That would be my tap. So this pad here is basically the size of the via I'm going to use. And I've got 2 legs here that are basically the input and the output or the pass-through of the main signal. So here on this thing, I can show you here, basically this is the tap. And you can see the via that I left into place. And the blue pads are basically my capacitors to decouple, and then I just go down here. And you can see I've already done some length tuning on these guys so that both of these legs are the same. So anyway, this is a real-world example of sometimes you actually have to add in net ties and use the differential names as opposed to getting rid of them, which is what xSignals is usually used for. So I think with that, I'm going to go ahead and turn it back over to Paul. So.
All right, thank you very much. I'll grab the screen over here. So let's bring this back here. So the next thing we're going to talk about is match length tuning, but what I want to do before we do that is give a very quick primer on differential pairs. So what I'd like to do at this point in time,
yes. We can't see your screen yet.
Can't see it yet? Oh, that's right. They still got this little, I always forget that just because I changed the monitor to me doesn't mean I'm there. There we go. Let's do that. All right, there it is. Hopefully you can see the screen now, Tom?
Yes, we can. Thanks.
All right, excellent. Thank you. All right, so what we're going to do over here is talk about the differential pairs. And what I'd like you to do is take a look at what I've done over here. Because there is a correct way of doing differential pairs on the schematic side of things. And what I want you to do is I'm going to give a polling question and see which one of you guys know which one of these will actually work properly. So let's get that poll up here. Yeah, and I do apologize here if you didn't see this over here. Let me just give you guys a moment here to take a look at this. I don't think we can reopen a poll here at this point in time. The kind of the differences between each of these, and I probably should have done this before we did the poll a little bit, is that we have diff pair 1 with an underscore N and an underscore P. So we don't normally use, at least I don't normally use any type of white space in my names here, but unfortunately the underscores do get buried when you place those down over here. So we have this one over here with some directives. We have something very similar to the first one without the directives. And then you can see over here for diff pair 3, there's just P and an N without an underscore here. And then for diff pair 4, we just use an L and an H, which is another convention here. And all of these, except for diff pair 2, had a directive here with it here. So what I'll do over here is we can just kind of ignore the results of that since you guys didn't have a shot at it. But if you guessed diff pair 1, that's the correct one. Okay. So what's wrong with the other ones, or are they wrong? If you're trying to get the differential pair to go from the schematic side over to the PCB side, Altium requires certain things. So in this case over here, what you want to have is a prefix. So when I'm talking about the prefix, diff1 would be the prefix, followed by an underscore P and an underscore N. So you'd have the same prefix here, but you have an underscore N and underscore P. And then you need to put down the directive as well. So diff pair 2, its naming convention is correct, but there's no directive to this. Now, in terms of the directives, they're really easy to do. So once you've got the name here, it's a matter of going into place, directives, and then from directives, you want to go into differential pair, and you just simply drop these down over here as such, and you'll get those here. So I'm going to delete these here because I want to show you what happens when we do the ECO. The third part, these over here, unfortunately, they won't work, and you'll see why here in just a moment. First, Altium will not recognize these, even though these are what I'd call valid differential pairs. These won't necessarily work when you go through the ECO process. That's not to say we can't correct this afterwards. I'll show you how to do this on the PCB side, but from the schematic side, this won't work during the ECO. So let's take a look at that here. I'm going to go into Design, Update PCB Document, and let's open this here. And I'm going to turn off these other ones here for now because they're not really applicable to what we're trying to do. What I want to do is focus you on the the 5 different ones that you see here. So notice that the first one that's called diff1 is just called diff1. So even though we had a diff1 underscore N and a diff underscore P, the problem that we have with that, or Altium recognized that as being a diff pair, so it's not even a problem. It recognized it as being a pair, as opposed to diff pair 3N and 3P over here. Altium does not recognize that as being a single pair. It actually only sees one side of it. And the only reason it's listing it over here is because it sees the directive. And the same thing with the underscore H and the underscore L. So if we were to actually execute the change here, you'll see that the only one that's going to get pushed through is the diff1. These other ones are going to complain. And if we looked at the compile, by the way, it will complain there as well. So it's only recognizing this to be one of 2 pins. So just be aware of this configuration. Now, so that I think I've kind of beat that part there enough. Let's talk about being on the PCB side. You may be a layout designer where someone has given you the design, you're not authorized to change it, or if you have to change it, that's going to require some type of additional ECO and or review, and that's not the thing you want to go through at this point. But if they've at least used the proper, let's say P or N or H or L, there's some things that we can do here to allow you to create those here on the PCB side. So let's take a look at that here. I'm going to go into the differential pairs editor. So again, set up in the very similar fashion as all the other setups here. We've got our classes, we'll have our diff pairs here, and those things that make up the diff pair. Let's click on, there's 2 different ways to do it. The first one I'm going to do is I'm going to click on add. And the add one is kind of an interesting one because it allows you to create differential pairs out of any 2 wires, which would not be very realistic because half the battle with differential pairs is making sure that the 2 wires are running right adjacent to each other to minimize noise issues. It's called common mode noise. So if you're just picking them arbitrarily, you're not going to get a whole lot of use out of that. But you can click over here. So for example, if I wanted to do diff 3N, so it wasn't set up properly for it to get pushed over and recognized by Altium as a diff pair, but I can still create it on this end. So I can go over here and I can click on diff N. Yeah, that's the positive net. Let's make sure we do that right. So the positive net will be diff pair P, and then over here I'll have diff pair N. Now, if you have a really, really long net list, this is going to be a little bit painful. So, but if you're only creating one of them, it works just fine. So I'm going to call that diff pair 3. That's the name that you'll see up here, and I'll press OK. If I zoom in over here, we may also be able to see those pairs. There we go. So there's the one that came in from the schematic side. Here's the one I just created. Okay. And I'm going to create another one from the net here as well. So there's a tool here. So if you have a bunch of these, and that's the thing is if you have a whole bunch, you don't have to go through this craziness of adding them individually. You can use this little wizard down here, and as long as you put the right information in there, like if you just say, hey, I expect the N to be an N or a P, it will actually find those things here for you, and so you can select them. Again, be a little bit careful about, sometimes I've found that it will either create another diff pair that already exists, or it'll overwrite it. I'd just say just be careful of that type of thing there, but you can press execute. Let's see what happens here. So you can see I do have a little bit of duplication there. It's easy enough to delete those. So if I want to say, no, I don't want this, I'll press yes. I have a diff pair 2, that's fine there, and I'll keep my, I'll delete one of the diff pair 3s. So easy enough to do. I can also create classes, and in turn, I can also create rules with it as well. The reason I have to do that is that if I want to do any diff pair routing, well, I've got to actually declare the diff pair, because Altium will not allow me to use route interactive differential pair routing. So if I try, for example, to click on this one, which was diff 4, which I've not declared, it's going to complain saying I don't know what the second pin is. So I'm going to start over here with diff pair 3 and show you a couple of pointers here. Come on, don't be this way. You are going to be this way. Let's pick the other one here. And again, sometimes I have found it's been a little bit persnickety, which I can quickly remedy here in a moment. So when you start off in the route here, one of the things that can happen is that they split off like this. And that, again, defeats kind of the purpose of the differential pair. You really want to keep these closely coupled as much as possible, because number one, there's impedances involved with that. But number two, the reason you're doing this is you're trying to also minimize the noise impact. So as this is going along, if your board is impacted by noise, the idea with the differential pair is that it's sending out an equal and opposite piece of information. And when it goes to the receiver, and as long as it meets the setup and hold time, the receiver will declare that to be valid and take it in. If there's noise that goes on there, the idea is that the noise is going to be equal on both lines. And so when the receiver gets it, it will reject it because it's not equal and opposite. As we're moving along here, I'm going to just kind of zoom us out a little bit here. So we want to keep this line moving here, okay, and keep it parallel. As we start getting into this curve here, one of the tricks that Tom taught me is that before you get into the curve, lock down what you've got over here, and then you can start getting into your curve here. Actually, I'm going to backspace this up just a little bit, just so that we can, so that I can get a little bit closer in there. So now I've got this locked down, and now I'm going to start my turn here. So just like any other route that you do in Altium Designer, the shift space bar will allow you to toggle through the different mechanisms that you've got. So you can do shift space here to go to rounded 45, shift space again to go to orthogonal, shift space again to go to curved orthogonal, and then you can go shift space again, gives you your 45 degree. So once I've got bring this in on over here, what I've also found is that just before you start making your entry into this, you may want to click one more time, and then you can bring it in. Now, this may not look super clean to you, and sometimes if you get it just right, they will branch off just beautifully. We have bigger problems anyway, so when he comes over here, one of the problems we got is that this inner jog is longer than the outer jog, so that's something we're going to have to fix here. And then I'm going to do one more of these very quickly, and then we'll get on to our match length tuning. So, pardon me, got to use the right tool. Tools, interactive differential pair routing. So let's, we're going to do this again. Okay, so if it does do this where it's getting a little persnickety about the differential pair, that's not a problem. I'm going to save this, and similar to what I do with the xSignals, I'm going to close this one out and just bring it back up again, and it should recognize it. Okay, so let's get back on into that here. All right, and hopefully it still has it. So let's go back here. If not, I can always add it in. So there it is. There is our diff pair. There is our diff pair 2. That's our diff pair 2. Let's use that. Sorry, we already have that one. Let's do diff pair 3. I didn't save it. Okay, fine. PT, I thought I did. Oh, there it is. It's already, I'm sorry, it's already there. All right, let's not get rushed. Let's do this. Let's go into our route, differential pair routing, and we'll click on this. The other one is there. It's just that it was being masked off. So again, I'm going to click down to get these two together. Actually, backspace that. We'll bring this here. I'm also on a really tight snap grid, which is moving it around a little bit more than I want to. So before I start the angle here, I'll lock it down. I'll hit my shift space bar, my space bar. And that's one of the things I didn't mention too, is that with the space bar, you can do what's called end or begin. So in this case over here, I am doing a start 45. If I hit my space bar, so not holding down the shift key, I'm just hitting the space bar, this is called end 45. So the space bar by itself will allow you to adjust that or toggle it in. And so I'll bring this over here as such. I'm going to click on it. And again, I'm going to bring this in, and boom, I'm done. So that's kind of what I want to show with that. But let's get to the match length tuning part. I'm going to do a Shift C so we can see everything at this point in time. Now, we've got actually three issues over here. The first issue that we've got is that, as I mentioned, because we did this jog downward, and we did this on purpose so we could show this, each one of these is not matched up properly. So if we look at diff pair 3, we can see that we actually have quite a bit of length difference between these two individual wires here. So we're going to have to correct that. And of course, between diff 2 and diff 3, we also have a major difference between those as well. So how do we fix that? Well, we're going to start off with the match length tuning. So what we can do here is, since I've already got this one up here, I'm going to take diff pair. Actually, I'd like to do diff pair 2 because the rule is already kind of set up for it. So we're going to take diff pair 2 and we're going to start match length routing. Just before I do that, and you'll see this here in the match length tuning, I'll look at design rules because there's a rule here that I'm going to lean on for this. And it is not the match length rule, it is the length rule. And in the match length rule here, I just want to make sure that my name is correct because sometimes this gets changed during when we type those things in. So as I go into here, let's just do this. And then what nice part is as I start typing it in, it finds it. So this name did change a little bit. I'm glad I checked that. So this is the diff pair that I wanted to do it for. So in diff pair 2. And this is the minimum and the maximum. And if I want a very specific location between the two, like a preferred, I can do that in the match length tuning itself. So I'm going to press OK here. All right, and let's get some match length tuning going. So in match length tuning, I'm going to go into route, and then I'm going to go down further about halfway, interactive diff pair length tuning. So I'm going to start this over here, and I'm going to click and begin. So let's zoom this here. Okay, and there it is. So there's the line, and it starts to go. I'm going to hit the tab key. This is one of the nice features of Altium 18, is I can kind of stop this. I know I buried this a little bit here. It's going to show you kind of an is-was situation, what's going on with each one of these. It's also going to show you the progress that's going on here as well. But more importantly, when I hit the tab key, I can get into the properties. And there are three basic properties that I can work from. I can work manually, where I pick an arbitrary number, and from that arbitrary number, I can clip it. I can also go from the rules, and this is the rule I actually want. So I'm going to leave it on the rule here. And by the way, what I can also do here is, even though I have a min and a max length, here's where I can do my preferred. So I will tell it to clip it to 5600. And then lastly, later on, if we won't have time to do this, but if I was going to do the second one over here, I could click on this one over here and say, hey, use diff pair 2. The only reason you just don't see diff pair 2 over here is because that's the actual one that I'm on here. All right, so we're going to do it from the rules. And then what you're going to see are the patterns. So there's mitered lines, mitered arcs, and there is also rounded here as well. Now, Tom's going to tell you that he prefers the rounded version of this, and he'll explain to you a little bit more why. But the mitered arcs here is a combination, and that's what you're seeing over here. It's a combination of arcs and lines, whereas the mitered lines are just strictly those arcs. And so as you click on these here, you can see how they change up. I'm going to do the mitered arcs. The last thing over here is the amplitude, space, and the miter. And you'll also notice the shortcut keys have also been listed here too, which is really, really cool. So the comma will make it smaller. The period will make it longer in terms of its amplitude. I'll demonstrate that here in a moment. So that means basically the height of it. The space over here can be shortened or lengthened using the 3 or the 4 key. I'll also demonstrate that. And then also the miter here, so you can make it look really squarish or make it look much more round if you want to. The one thing I'll mention about the spacing is you want to be careful about the spacing, because in high-speed design, you can couple onto your own wires. So if these wires are close enough to each other, usually the rule of thumb is that if they are less than 2 trace widths, you might have a coupling opportunity over here, even though they are the same wire. So be a little bit careful about your spacing. I'm going to hit the key here to continue. So as you can see, I'm going to go along. And once I've gone there, it hits the green because it does clip off there. It looks like my clip moved. Again, change this over here to 5600. Sometimes that does happen. See if that'll fix it there. And so now it did correct itself. So if I start hitting for the amplitude, if I start hitting the period over here, you'll see it'll grow. And when you do this, don't keep firing at it, because Altium has to do a little bit of a refresh. So hit the key, see what you get. If you want to continue with that, then you can do so. Of course, the comma key will make this a little bit smaller. Of course, for the spacing, if I hit this here, I will get a little more spacing. So you can see as I slowly tap this, Altium's updating this. And then lastly, with the miter, I can do it 1 or 2. So I can make these look really, really round if I want to do that. Now, here's the thing. I'm pretty happy with what I've got here. I'm going to click on it, and I'm done. Here's the issue with this. Unlike the single match length route period, once I am done with this, if I don't like the result here or somehow I screwed this up here, I've got to either hit Control-Z to undo it, and then go back into the tool and fix this up again. Or later on, if I have to fix it, I'll have to delete it, put those lines straight again, and then run the match length tuning. It's a little bit different when it comes to the single pair. So let me do a Shift-C here to get us out of that. I'm going to do a very, very quick route from P4 all the way over here just to demonstrate the minor difference. Okay, so now I've got the single line, and then unlike the, let's go to here, route, unlike the interactive diff pair length tuning, I'm going to use the interactive length tuning, which is for single lines. So I'm going to start doing this here, and let's go there and click on that. And I'm going to cut this here short, even though I have a total length of 9,999. I'm not going to go all the way down. Really, what I want to show you is that once you're done with what you want to do here, because really all of the options are the exact same as a differential pair. It's just that once you are done with this, you can actually take this and stretch it out. So if you need to stretch these out, or maybe you want to make a little bit more room, you can do something of this nature over here. But you cannot do that with the differential pair lines. The last thing I want to show you over here before I turn it over to Tom is that, yes, we have now done match length tuning based on the rule. But if we look over here onto our design, okay, so this is differential pair length 2, we're going to see that we still have quite a bit of gap over here between the N and the P, and we want to fix that. So even though the match length tuning, these are pretty much equal, because as we were going in here, we were going out, going in and out. And so it was pretty much equal at that point in time. It's just that once we got over here to this bend over here, that's when the trace lengths got much different. And again, one of the rules with differential pairs, you want this to arrive at the same time for the receiver. So how do we fix that? Well, there's a little tool that a lot of you have probably been using, and we're going to take advantage of that. You may know that if you start a route, okay, and you go on in here and you start doing something like this, you know that once I'm done with this over here, okay, it's going to remove the original piece. That is a loop removal capability. And a lot of people use it to trim up things. And that actually is a preference, and I'll show you where that is here really quickly. So under the PCB editor, under interactive routing, it is turned on by default, and you can see automatically remove the loops. And that is what we're going to take advantage of. So the intention over here is to now add a little bit of an extra length to this so that I can match these up rather close. And as a matter of fact, it did a pretty decent job just by blindly putting this together. But you can match these up rather tightly. The last thing I'll show you here is that if you want to do that, zoom it in pretty close, keep your eye down here on the two differential lengths. And then what I'm going to do here is I'm going to turn off the snap to grids. And from there, I can really make some really minor adjustments to that to get it where it needs to go. Okay, so, and as Tom will tell you that he spent hours sometimes doing this because they've got to get it sometimes below 1 mil for some of these very high-speed designs that we've been asked to do. So you can see here, and even at this point in time, for most things, really probably even up to 10 gigabits, this is going to be pretty good. But if you're, you know, if you're someone like myself who really wants to be nice and clean, you can really zoom this in and protect and get it down to you know, a real accurate number. So, but this will work, and it's more than fine. And the last thing I'll mention before I turn it over to Tom is that, you know, we have it a little bit easier here because these both came off at the same time. If you've got going through a pin grid array and you've got a little bit of a choppiness, you want to correct that match length tuning from the very get-go. You don't want these two signals to travel separately through the entire line there. As for the rest of this over here, the procedure would be as follows. We would basically click on this, match length tune this line to this one over here, or to the rule, and then we would do the same procedure again at the very bottom here, where we would add in a little bit of a jog so that we could correct that. And you don't have to have one large jog, by the way. You can have multiple little jogs too. So if you're a little uncomfortable with this sticking out so far, there's nothing that stops you to put in several little jogs to keep it close together for the noise for the noise issues. So with that, I'm going to turn it over to Tom. So Tom, I'm going to make you the presenter here again.
Okay, let me see if I can get my screen.
There you go.
You see it?
Yep, I do see it.
I just want to take a quick aside here. I had several comments in the questions about why I picked such a weird shape for my taps on this. These were gigahertz level signals, so having a very clean impedance routing was pretty important, and we had to make some trade-offs because of that. So several people said, well, why don't you just go through the via? I could have done that, but then we would have had introduced, a wider trace spaces and different impedances. This basically maintains my nice straight pass through of copper and then taps off to the edge. So it's about as minimal of a Heisenberg uncertainty as you can get. Try not to affect your signal by looking at it. So that's why this came out kind of weird. So I just want to show a couple quick examples of some of the things Paul was talking about here in this very old DDR3 design. I like to use the rounded, as Paul mentioned, and the reason I do that is mainly from a signal integrity point of view. If your routing lets you have a fair amount of space between your traces, it's not that big of a deal, but sometimes you're just going to have to get close. You just can't avoid it. And if you're doing that and you've got a rounded signal, the only perfectly parallel point is tangent to that line. You don't have a large area of parallelism, and therefore your crosstalk will be minimized. The downside, of course, is purely rounded arcs are harder to work with. If you find you're going to have to do a lot of adjustment or whatnot, the miters are working better. But from a signal integrity point of view, rounded is the way to go. Another kind of trick I use is if you're having to route two lines or match length two lines that are close, kind of alternate where you do the routing or the tuning. So you started this one here, and then I started this one here. So you can see I kind of was able to overlap the distance instead of having to get them far apart. And you can see I kind of did that here. I did these two here, but then I just didn't start this one until it was farther along. Once again, may not be perfectly optimal, but you got to bow to real world necessities. I think there was an example up here that Paul liked. Here's a differential pair coming off of two pins, and you can see, it doesn't get really balanced off again until here. This was as soon as I was actually able to introduce the length tuning between the pairs. And this is a little far. You typically don't want to have this much space, but once again, you've got to do what you got to do. And sometimes you're going to have a lot more impedance mismatch, but you're going to have your signals arriving at the same time. And then also up here, since it was basically a C shape, I had to really add length to the inner trace. And so you can see you can end up sometimes with some pretty weird stuff that doesn't really look like it's differential pair, but so you kind of got to do what you got to do. It looks like we're running out of time, so I'm going to just go ahead and turn it back to Paul.
Okay, thank you. I'm going to put back my screen over here.
And don't forget to turn it on.
Show my screen. Very good, thank you. And I'm going to bring back over here my current slide. There we go. All right, so I know we're pushed a little bit here for time, and as usual, we're trying to get as much into you as possible in the hour here. Why do we do these things? Because we know that you're here for a reason. And the reason you're here is because you want to learn more about Altium's tool capabilities for high-speed design, right? That's what Altium touts. And hopefully you can see that these are really useful tools. I mean, they're critical for us in order to do the type of work that we do. And also to see some real-world examples over here that Tom has been doing here, especially for the past year. So what do we do here at 9.Connects? There's a lot of different things, but recently we have dug deep into DDR3 and DDR4. It's really become a niche for us. So if you're having some issues with that, feel free to contact us. We can certainly provide either services and or some training, which we call coaching, to assist you with these type of designs. And we're just going to continue to dig into these things. We have found that this is an area that a lot of people are struggling with, a lot of people are trying to get into. And again, if it makes you feel any better, the fact of the matter is it's still kind of new for everybody. And even Rick Hartley will tell you that when he's done it, it's only in the last decade or so that it's starting to make a lot more sense to him. So we're all trying to struggle through this and trying to figure out how to make the high-speed stuff work for us. And unfortunately, these days, as they say, either you have high-speed problems or you don't know yet that you have high-speed problems with that. So, of course, if you want to check us out, feel free to take a look at 9.connects.com, and you can find out more about our services and our training and our coaching. And, of course, there's always opportunities there, so if you want to contact us, feel free to do so. So with that, I know we're a little bit past the hour. I was hoping to get to a few more questions today, but obviously we're at the hour. We'll keep this open here for an extra 30 seconds or so. So if you wish to write in any additional questions, feel free to do so. And then Tom and I will look at those here this afternoon and start getting together a Q&A. Thank you so much for joining us here today, and we will see you next week.